All right, let's dive right into this explainer. Today, we're looking at something that honestly feels like it was pulled straight out of a sci-fi novel, but it's happening right now. We're going to explore how Google is using its Gemini 2.0 model to build a multi-agent AI co-scientist. And here's the absolute game changer. This isn't just some AI that summarizes text for you. No, it's a system literally designed to generate novel, testable research hypotheses. We're talking about a virtual collaborator that could legitimately accelerate the clock speed of scientific and biomedical discovery.
Now, to really wrap our heads around the problem this tech is trying to solve, we got to ask a super practical question. How on earth can a modern researcher navigate the sheer, exponential growth of scientific literature? I mean, thousands of papers drop every single day. It's physically impossible for one human being to read all that, let alone integrate complex insights from totally unfamiliar domains outside their own specific niche.
And honestly, this brilliantly illustrates the breadth and depth conundrum researchers are facing right now. Just look at the 2020 Nobel Prize in Chemistry for CRISPR. That massive breakthrough, it didn't happen in a silo. It demanded serious transdisciplinary expertise, pulling from microbiology, genetics, and molecular biology. Modern breakthroughs require crossing the boundaries of traditional fields. And let's face it, that is incredibly difficult for one human mind to master all alone.
We've got a lot of exciting ground to cover in this explainer today. We'll start by looking at the modern science bottleneck, then meet the AI co-scientist itself, dive into test-time compute, check out some mind-blowing real-world lab validations, and finally, look at the future of discovery.
So, let's kick things off with our first point, the modern science bottleneck and the unmet needs in scientific discovery. The crucial takeaway here is that your standard literature review and deep research tools, well, they really just summarize what we already know. Right? They're great for catching up, but scientists need a tool that actually mirrors the scientific method itself. They need a system that doesn't just read the past, but actively helps uncover original knowledge and formulates demonstrably novel research proposals tailored to very specific goals.
And that brings us right to our second section, meeting the actual AI co-scientist built on Gemini 2.0. Okay, so here's how this system actually builds a team of virtual experts. It's really important to note that it's not just one giant AI model trying to do everything at once. Instead, the human scientist provides a natural language goal, basically just typing out what they want to achieve. Then, a supervisor agent steps in. It parses that goal and literally organizes a virtual laboratory of specialists, assigning them to a worker queue to tackle the problem step by step. Now, take a look at this coalition of specialized agents. We've got generation, reflection, ranking, evolution, proximity, and meta-review. Acting under that supervisor, these agents actually engage in self-play-based scientific debate. Yes, they literally argue with each other. They use automated feedback to evaluate and refine their outputs, which creates this amazing self-improving cycle that results in increasingly high-quality, totally novel hypotheses. Which leads us perfectly into Section 3, the engine behind all this, test-time compute and reasoning.
The really profound concept here is test-time compute scaling. You know, in traditional AI, you ask a question and boom, you get an instant answer. But here, the system is explicitly designed to take its time. As the AI spends more time running those ranking tournaments between its internal agents, recursively critiquing itself and evolving its outputs, the science it generates actually gets better. It literally scales compute to think harder and longer.
And the impact of that extra processing time is pretty striking. If you compare standard Gemini 2.0 to the AI co-scientist, the co-scientist uses an ELO auto-evaluation metric. It's very similar to how chess players are ranked, and it's derived right from those internal agent tournaments. The data shows that getting a higher ELO rating from these debates directly translates to a much higher probability of getting correct answers on incredibly challenging benchmark questions, like the expert-level GPQA diamond set.
Just look at this number, 15. The team didn't just rely on automated benchmarks. They actually had 7 human domain experts curate 15 highly complex, open research goals in their specific fields. And get this, the AI co-scientists not only outperformed other state-of-the-art models, but as it spent more time reasoning, it actually surpassed unassisted human experts in its potential for novelty and overall impact. Just let that sink in for a second.
All right, now for the absolute coolest part of this explainer, Section 4. Taking this out of the computer and validating it in the actual lab. Because, let's be real, it's one thing to generate fancy text on a screen, but it is an entirely different beast to move to actual physical biology. To prove the system wasn't just hallucinating, scientifically plausible-sounding jargon, researchers took the AI's novel hypotheses directly into the lab. They validated these proposals across 3 incredibly complex domains with expert-in-the-loop guidance. Let's break down each of these real-world biomedical applications. First up is acute myeloid leukemia, or AML. To really appreciate this, you've got to remember that drug development is famously slow and crazy expensive. So drug repurposing, taking a drug already approved for one disease and using it for another, saves massive amounts of time and money. But it's a highly complex task that requires vast interdisciplinary expertise just to predict what might even have a chance of working.
Well, astonishingly, when tasked with this, the AI co-scientist proposed completely novel repurposing candidates for AML, and the physical in vitro lab experiments actually confirmed it. The specific drugs the AI suggested successfully inhibited cancer cell viability at clinically relevant concentrations across multiple AML cell lines. The AI practically found a new weapon against leukemia just by reasoning through existing data. I mean, wow.
Moving on to the second case, target discovery for liver fibrosis. Identifying entirely new treatment targets is arguably even harder than drug repurposing, and it often leads to frustrating dead ends. But working alongside collaborators at Stanford University, the AI was asked to propose and rank hypotheses. The result? The AI pinpointed highly specific epigenetic targets, and when they tested these in 3D human liver cultures, basically organoids that mimic a real human liver, these targets showed significant anti-fibrotic activity. They were possibly even reversing the disease phenotype.
And now for our third case, which honestly is the ultimate mic drop. Antimicrobial resistance is a massive global threat, right? Well, a human lab had spent years making a novel discovery about how specific elements like CF-PIEs interact with diverse phage tails to spread this resistance. Crucially, they hadn't published this yet. It was a total secret. Researchers asked the AI co-scientist to explore this exact topic using only publicly available, decades-old open-access literature. Without any prior knowledge of the lab's secret findings, the AI independently rediscovered the exact same mechanism in silico. It did in a fraction of the time what took humans years to piece together. It's just mind-blowing.
So where does this leave us? Let's wrap up with Section 5, the future of discovery, including some limitations in our outlook. Now, to remain completely impartial here, we definitely need to talk about the system's current limitations. This isn't some flawless magic wand just yet. The researchers themselves note that it still needs enhanced literature reviews, way better factuality checking to prevent any subtle errors from sneaking in, cross-checks with external tools, and much larger scale evaluations with many more subject matter experts. Science absolutely requires rigorous proof, and this AI is still very much a tool that requires human oversight.
But to address those very limitations, Google is opening up a trusted tester program. They're actually inviting research organizations worldwide to join a collaborative, human-centered evaluation process. They really want to responsibly explore the strengths and limits of this assistive tech by putting it directly into the hands of the broader scientific community.
So, I'll leave you with this final thought to ponder as we wrap up this explainer. We are looking at a fundamental paradigm shift where AI is no longer just a fancy search engine, but a true active collaborator. If an AI co-scientist can already generate testable, potentially Nobel-worthy hypotheses by debating itself and reasoning across millions of documents, what grand challenges will human ingenuity solve next with an AI right by our side? The bottleneck of modern science might just be breaking wide open. Thanks for joining me for this explainer, and as always, keep learning.